You study about the technical report, vibration analysis of a single cylinder vertical diesel engine mounted on a steel chassis. We have one numerical example as well as a VBA program also how to calculate these answers for these questions. Introduction. This report presents a vibration analysis of a single cylinder vertical diesel engine mounted on a steel chassis frame. The focus is to determine the amplitude of vibration at a given operating speed. So we might be knowing the given operating speed, and we need to find out what's going to be the amplitude of vibration and find out the speed at which resonance occurs. We need to find out the speed at which resonance occurs also. These two are our solution we need to find out. Considering the system's dynamic parameters and damping effects. So the problem description: mass of the engine and chassis is 400 kg, static deflection due to chassis is 2.4 mm, and that's going to be 0.0024 meter, reciprocating mass 18 kg. The reciprocating mass, that's the one going to cause vibration. And length of stroke, that's 160 mm, that's 0.16, that's going to give us some eccentricity about the mass. And damping coefficient of dashpot, operating speed 500 rotations per minute. So objective is to calculate the amplitude of vibration at 500 rpm. What's going to be the amplitude of vibration at 500 rpm? Determine the speed at which resonance occurs. So we need to find out the speed at which resonance occurs and amplitude of vibration at omega equal to 500 rpm. Okay, these two we need to find it out. So first thing is analytical approach: natural frequency and stiffness calculation. Use the static deflection due to chassis Y to find the equivalent spring constant. We know force is nothing but stiffness into displacement. So displacement they have given, that's 2 mm, and force also that's a weight what we have got from this problem, that's 400 kg, right? So mass is 400 kg, gravity we know, and deflection also we know. So from that we can come to know the stiffness. Once we know the stiffness, from stiffness and mass we can know the natural frequency. Then excitation frequency we need to find out. That's we are getting it from the 500 rpm. That's 500 is the number of rotations, and 2 pi by 60, that from minutes to seconds we are making it. And frequency ratio, that's omega operating frequency to natural frequency, that's around 0.819, that's close to the natural frequency, right? If beta is 1, that's resonance occurs. Exciting force due to mass is, we need to calculate the radius of crank, that's eccentricity, and this is the force. This reciprocating mass 18 kg, r is the radius, and omega square is the speed at which it rotates. So this is a force. So design parameters, we know the critical damping coefficient, and we can find out the damping ratio, that's around 0.039, it's under damped. So we know the vibrations, amplitude of vibration 500 pm, that's, it's like displacement we know, that's nothing but that's proportional to the force and indirectly proportional to the stiffness. And this is the dynamic one, so we need to consider the frequency ratio as well as damping also, damping parameter. So from that we can come to know what's the amplitude of vibration, that's around some 7.2 mm. So we know that's initial 2.4 and static difference 1.2 is the vibration amplitude. Resonance speed means we should know what is omega and omega n should be equal. From that we can calculate the number of rotations per minute. So these are the results. Let's start discussing about the problem. Alright, today we are analyzing the vibration in diesel engine mounted on steel chassis. Our goal is twofold: find the vibration at amplitude at 500 mm and the speed at resonance. What's the starting point? Let's know the key data. The combined engine chassis mass is this much, static deflection is this much. So this tells us about something about the stiffness. Because the weight compressed the chassis by 2.4 mm, we can use Hooke's law to find out the equivalent spring. Once we know the spring, now we can find out let's find out the natural frequency. And natural frequency we know, that's going to be 63.93. What about the operating frequency? Operating frequency we can calculate from the 500 revolutions per minute. Angular frequency, then calculate the frequency ratio. And once we know the ratio, next exciting force is coming from the reciprocating mass. Exciting force is coming from the reciprocating mass and stroke radius, and then omega square. So we can come to know what's the reciprocating force. What about the spring? What about the damping? Damping, we know this one. Critical damping also we can calculate it. So damping ratio we can get it, and amplitude of vibration we can find out. That's going to be around 7.2 mm. Then now for the resonance speed omega n, from that we can come to know. So vibration amplitude of 500 rpm is 7.2 mm, resonance speed is 610 rpm. This tells us the engine will experience highest vibration amplitude near 610, and the damping helps keep the amplitude reasonable at 500 rpm. Breaking down like this makes it much clearer. Now let's talk about a little further. Alright team, we did all the calculations, but let's talk about what each step really means in the real world. I want to know why even we calculate stiffness from static deflection. Imagine the engine sitting on the chassis like a heavy box sitting on the resting on the spring, right? The static deflection shows how soft or stiff the chassis spring is. If it deflects a lot, it's soft. If not, it's stiff. The stiffness is the key because it tells us how the chassis will respond to vibrations. So the chassis is like a spring that pushing back against engine's weight, right? Now moving on to the natural frequency, that's the rate at which the system wants to vibrate, bounce and back, forth and bounce back and forth. If you give it a nudge, like a playground, a swing that wants to move on its own pace. So when we find a natural frequency, we know the rhythm system prefers to vibrate at, right? You got it. Now the operating frequency is how fast the engine shaft is spinning. That's how fast the force from the reciprocating force is pushing and pulling. And comparing the operating frequency to natural frequency, that's frequency ratio. Those ratios tells us how close the engine's shaking matches with the system's natural bounce. When these two are close, you get resonance, and that's when vibrations get large and dangerous. Why does the reciprocating mass create such a big force? The mass moves back and forth every revolution, creating a centrifugal force. Think of it like a weight spinning on pulling out. This force is actually what pushes chassis to vibrate, right? How does that fit in? Damping. Damping is like a surge on your car. It resists the motion, turns the vibration to heat. Vibrations into heat, slowing down the shake. Without it, the system would keep vibrating longer and more violently. That's why the dashboard with the damping coefficient helps keep vibrations check. Damping ratio tells us how effective that is. The amplitude we calculated, that's for how far the engine actually moves during operation. That's 7.2 mm, right? That tells us the real displacement during the operation under 500 rpm. Too large and it could cause damage or noise. And the resonance speed, that's when the system's natural frequency matches the forcing frequency, causing those big shakes. At 610 pm, the engine will vibrate strongly if not controlled. That's why we want to design and operate away from the speed or add enough damping. So every step links math with how machine feels and behaves in reality. Let's talk about what each calculation really means. We want to calculate the numbers from the machine's real behavior. Why do we start by calculating stiffness from the static deflection? Imagine the engine sits on a spring, the chassis acts like a spring. When the engine pushes down, the chassis compresses. 2.4 mm deflection shows how soft or stiff the chassis is. The bigger deflection means softer chassis. The softer chassis bends easily. A stiff chassis resists bending. Stiffness that tells us how strong the resistance is. This matters because it affects how the system vibrates. This matters because it tells us how it affects the system vibrates. What about natural frequency? What is it basically? Think of swing. If you push it once, it swings back and forth naturally. So natural frequency is how fast it swings on its own. It depends on the stiffness and mass, correct? The heavier or softer the system, lower the natural frequency. If heavier means its own mass resists its motion, softer means it will not try to pull it back quickly, so it becomes lower frequency. Now the engine starts rotates at 500 rpm. That gives us the forcing frequency. So this is where the forcing frequency comes. Forcing frequency means how fast the force acts. Forcing frequency means how fast the force acts. The forcing frequency is how often the engine shakes the chassis. Comparing the forcing frequency and natural frequencies gives the ratio beta. So that ratio shows us how close we are to the resonance, and what happens if beta is near 1. The system vibrates strongly and small force causes big vibrations. Why does the reciprocating mass cause vibration? The mass moves back and forth. It creates a force like push and pull. The force shakes the chassis engine. It's called the exciting force. How does the damping fit in physically? Damping is like shock absorbs. It resists motion. The damping slows the motion, vibrations. Yes, that's right. Because the damping turns vibration energy into heat. What if there is no damping? Vibrations last longer and grow larger near. It lasts longer as well as grow larger near resonance. The dashboard gives us the damping coefficient. Yes, comparing that to the critical damping gives the damping ratio. If low rho means little damping, high rho means more damping, strong damping. Right. Now the amplitude we calculate sources how far the engine moves. So of 7.2 mm up and down. That's the real vibration amplitude during operation. Why do we care about the resonance speed? At resonance, vibration can become large. The resonance speed is 610 rpm here. Operating near resonance can damage the machine. So we want to avoid that speed or add damping. Exactly, that's how we keep machines safe and quiet, right? I see how each step connects math to real machine behavior. This is the VBA program, and this tells us what's the mass and static deflection, gravity, damping coefficient, operating speed, and this is the reciprocating mass, crank stroke in meters, then find out the natural stiffness value, then natural frequency, then beta ratio, then find out the R value, exciting force, damping ratio, amplitude calculation, square root of 1 minus beta square, that is P naught by K, denominator, numerator and denominator. If you divide it, and you can see the stiffness value is this much, and operating frequency, natural frequency, amplitude vibration, all these things we can find it out. And alright, today we write a simple VBA code to analyze vibration. Where do we start? We begin with the inputs, mass, deflection, speed, damping, all from our real machines. The code starts with diamonds like a dim as double m equal to 400. That's the mass. So for the deflection, same for deflection, gravity, all values go in. What comes next? We calculate the stiffness value. That tells us how stiff the chassis is, just like we did by hand. Then we calculate the natural frequency, that's the swing frequency of the system. After that, we get the operating frequency from RPM. From RPM we can get the operating frequency. Now we compare them with the beta ratio. This shows how close we are to the resonance. Whatever exciting force, we calculate the radius and then use this formula to calculate the reciprocating force. That's the sake caused by the reciprocating parts. We calculate the damping ratio. That shows how the damper is compared to how strong the damper is compared to ideal damping. And then we put it all together, amplitude we are finding it out, then we show the result. So let's talk about the real troublemaker vibration. That's unbalanced mass. Real troublemaker mass, unbalanced mass. Yes, you mean that small piece inside the engine that moves up and down? Yes, that's the reciprocating mass. In our case, 18 kg, and it doesn't move evenly. Why not? Doesn't go up straight and doesn't go up straight and down. It moves, but not without force. As it speeds up, creates something called inertia force because it resists changing direction. Every time it reverses, it tugs engine block. This tug becomes vibrating force. So faster the engine speed, stronger this force. That's because the force is proportional to the square of angular velocity. As you see, the force is proportional to the square of the angular velocity and the radius and mass. Every time it reverses, it tugs the engine block. This tug becomes vibrating force, right? Where does the arc come in? That's the half the stroke. That's how the stroke radius of the motion path. Think of it like a circle. The piston moves linearly, but the crank moves in circle. So we treat them back and forth motion like a spinning weight. That's a trick. Unbalanced piston behaves like a spinning weight and the pulling on the chassis. What's it shakes? That's what the shakes the machine, right? That shaking force is periodic. That repeats every rotation, so it's harmonic force. So if the engine rotates 500 rpm, this means like this force is 5, so 4 cycles 500 times per minute. But the real punch is omega squared. When the speed doubles, the force becomes 4 times stronger. So high speeds can really shake things hard. That's why balance is crucial in rotating machinery. Even a small mass or high speed can cause serious vibrations. What if the engine was perfectly balanced? If it was perfectly balanced, the centrifugal forces cancels out. Centrifugal forces cancel out. No excess shaking, but the performance is rare. Even a few grams off can create a problem. Damping helps control that. But damping resists the motion, but it absorbs the energy from the vibrating system. But the best solution is balance first, damp second. So in our equation, the right hand side is the shaking force. This is the shaking force. Exactly mu me omega squared is the magnitude of the forcing function. It comes from unbalanced mass moving with angular speed. Unbalanced mass moving with angular speed. So the whole system is being pushed and pulled by this rotating imbalance. It's like someone pushing you back and forth at a certain rhythm. If that rhythm matches with your sync, you fly higher. That's resonance. What happens near resonance? The amplitude grows large. Even the small imbalance can cause vibrations. Knowing m or omega helps predict that. That's why we calculate and we use it to find out the vibration amplitude. Now I see the imbalance mass rotation speed are the drivers of vibration. Imbalanced mass and angular speed rotation speed are the drivers of the vibration. Rest of the equation shows how the system reacts. It means how you spin matters as much as what you spin. Ready to simulate in Excel. Let's talk about the term me squared. It looks small but it's powerful. It's a force on the right hand side. That's exciting force. It's what drives the vibration. Where does it come from? It comes from the rotating unbalance in the engine. Imagine a small mass not centered. It rotates around the shaft. You mean the reciprocating parts, the piston part of the crank, all that counts. Where we represent that m and unbalanced mass. What c is the eccentricity, the distance from the center of rotation to the unbalanced mass, like how far center the mass is, angular velocity, how fast the shaft spins in radians per second. So when you multiply them, when a mass rotates off center, it creates a centrifugal force, y square. The faster it spins, the more energy it throws outward, and it grows quadratically. If the speed doubles, the force becomes 4 times. That's why high engine speed machines suffer from more imbalance. This force is not constant. It changes with the time. It acts like a sine wave. That's why we write. So it pushes and pulls back and forth. That's what causes machine to vibrate periodically. If this force becomes input to vibration system, the rest of the system tries to resist it. So what happens when the forcing frequency matches with natural frequency? Then we get resonance. The amplitude becomes very large because the system responds strongly to that force. Even small m, if omega is high, can cause serious vibration. So in design, we either reduce m or reduce e or avoid operating near resonance. Those are the 3 strategies. Damping does not stop the force, but it reduces the response. I always thought vibration was random, but it was so predictable. me squared is physics. It tells us how much shaking energy goes into the system. Now I understand why it's so dangerous at high speed. Think of it like a hammer hitting the chassis over and over and force more harder. Without damping it near resonance, that hammer keeps pounding harder until something breaks or loses waves out. So this one term represents the root cause of all shaking. That's why we want to study it, we respect it. Now the equation feels alive. It's not just math anymore. It's every machine shakes. The term is spreading or shouting. This equation right here drives everything. It's heart of the force vibration. F m sine omega. This is an external force. This is called forcing function. There is vibration input from rotating balance. Where does it really come from? Unbalanced rotating parts. The mass that's not perfectly centered on the shaft. M is off center mass. Unbalanced mass. Even a few grams can matter at high speed. Even a few grams can matter at high speed. Is the distance. It's out center. That's called eccentricity. It's how far the mass is from the center of rotation. Omega is how fast it spins. Angular velocity is the speed radians per second. So the formula says the force is changing with time. That's what sine omega t means. The force is not constant, it goes up and down like a wave. Why is it sine wave? Because unbalanced mass rotates. As it means the direction of force changes in circular pattern. That's the vertical component of the force becomes sine wave. So if I tie a rock to a string and spin it, its up and down force on my hand is sine wave. Due to explain that's what sine omega t. What of omega squared? But why omega square? Omega, why is the omega square? Because the faster it spins, harder it pulls. Just not, but not just harder, it is exponentially harder. So if the engine spins twice as fast, the force becomes 4 times bigger. Yes, that's danger. Vibrations go fast with speed. So high speed engines are more sensitive to imbalance. At high speed, even a small imbalance force can cause large vibration. So this force repeats every cycle. It's a periodic. Every revolution brings the same force pattern. So if the shakes machine back and forth the same rate it spins. How the system responds, and this force goes into the vibrations equation. That's Newton's second law. Mass times acceleration equals upright force. So the system responds to this forcing function. Mass resists inertia, spring resists with the stiffness, and damper resists with the damping. But if the forcing frequency matches the system's natural frequency, then we get resonance, and the response can grow very large. M is unbalanced mass. Even a small imbalance matters at high speed. Eccentricity, how far the mass is from the center. Omega squared, spin speed square. Small speed increases, larger force increases. Sinusoid oscillation, the force repeats like harmonic force. The cause of vibration, it drives the motion, not the system itself. So if you know this force, we can predict how the system will vibrate. That's the power of this function. Once we know f of t, we can solve for x of t, then design for safety. I see now vibration is not chaos, it's maths driven by physics. The formula x, that's amplitude formula. This expression tells us the steady state amplitude of the mass spring damper system under harmonic force is by rotating unbalance, right? Caused by rotating unbalance. We will explore this in a long discussion style background, short and clear sentences. So alright, this equation is the key to predicting vibration amplitude. Let's break it down. Each term matters. Let's break it down. Each term matters. Numerator me by m into omega square, right? That's a forcing term. It's input force per unit mass. Input force per unit mass of the it lacks. Let's unpack it. M is unbalanced mass. Small mass off center matters. E is eccentricity, how far from the center the mass rotates. M is angular velocity, how fast the system spins. M is the total mass. Term me omega square is the magnitude of centrifugal force divided by m turns into acceleration or force per unit mass. So this is the shaking force. As it's the driving force. It's the driving force, source of all motion. It tries to make the system. It tries to make the system move, and the faster it spins, the bigger the force. It grows with omega squared. That's why small unbalances are dangerous at high speeds. Denominator, the system's resistance. Let's look at the bottom part. This looks like a combination of stiffness and damping effects. Damping effects and combination of stiffness and damping effects. Perfect. That's what it is. That's what it is. The system fights back with two things: elastic stiffness and damping. It resists the motion through its spring. It resists the motion through its spring. It resists the motion through its frictional energy loss. Stiffness part. This shows the difference between the system's natural frequency and forcing frequency. Omega n is how the system wants to vibrate. Omega is how the external force tries to make it vibrate. How the system wants to vibrate, how the external force tries to make it vibrate. So if those match, this part becomes 0. That's resonance. When stiffness no longer resists, amplitude peaks. If this is the stiffness part, if this becomes 0, if stiffness is 0, then amplitude becomes large, right? Okay, basically omega n and omega. Omega n is how the system wants to vibrate, and omega is how the system external force tries to make it vibrate. If that is stiffness part becomes 0, that means amplitude becomes very peak. And damping part. This is how the damping fights the motion. Rho is the damping ratio, how much energy system losses. The whole term throws The whole term shows damping role increases with both system frequency and force frequency. So near resonance, the damping becomes even more important. Without damping, the amplitude would shoot to infinity. Let's step back and interpret. The numerator is the strength of the force trying to move the system. Numerator is the strength of the force that's trying to move the system. That means how strongly it resists the motion. So x is the final resulting amplitude, how much system actually moves. So small denominator means large amplitude. At resonance, the stiffness resistance vanishes, amplitude spikes. Behavior across frequencies. Let's look at what happens omega changes. Omega denominator low, if denominator is large, small x, that's right. At omega equal to minus, stiffness cancels, the damping controls. High omega system's inertia dominates, x shrinks again. It starts low, rises sharply, and falls off again as one as thus sharp speaks this one. Why this matters? So this helps us predict if the machines will shake too much or not. Before running the machine, we calculate the x. If it's too high, we redesign. What if the x is too big? Reduce unbalance, smaller m or e, shift natural frequency, change the mass of stiffness, add damping, avoid resonance. Don't operate near my iron. M means the unbalanced force, E eccentricity is the forcing frequency, mass of the main system, natural frequency, damping ratio, amplitude of steady vibration. So we want to try to reduce the amplitude of vibration. Let's talk about tan phi 2 rho into omega n square minus 1. This is right here. It tells you when your machine moves related to the applied force. You mean it's not always in sync. Exactly, in force to vibration, timing is everything. The force may pull one way, but the mass might lag behind. The force might pull one way, the mass might lag behind. So the phi is the phase difference. Yes, it's the angle by which displacement lags behind the force. Angle by which the displacement lags behind the force. Why phase lag happens? Think of a kid pushing a swing. If you push or just right on, the swing goes higher, but if you push it out of swing, it barely moves or fights back. Same happens here. The system reacts when delayed depending on the stiffness and damping and speed. Breakdown of this formula. Numerator 2 omega 2 rho omega. This is damping, right? The damping term. The more damping you have, the more system resists motion. That means damping ratio omega natural frequency and force frequency. So the higher the damping means higher damping means bigger phase lag. Damping causes energy loss, delay in system's response. This term grows as the system becomes slower to respond. Denominator, this term compares how far the forcing frequency is from natural frequency from omega equal to 1, then term 0, that makes tan theta equal to infinity, so phi equal to 90 degree. Tan phi equal to infinity, right? If this becomes 0, tan phi infinity means phi is 90 degree. So at resonance, the displacement lags the force by 90 degrees. That's critical insight. It defines resonance behavior. Interpreting the phase across frequencies. Low frequencies means denominator is large, numerator is small. That means phi is 0. That's in phase with force. Lower frequencies. So the mass follows the force directly, like a car following your steering exactly. Near resonance, denominator is 0, that means numerator is non-zero, that becomes infinity, that becomes 90 degree, mass lags force by 90 degree. So they are quarter cycle out of the sync. So they are quarter out of cycle. The mass is always a little late, that's critical resonance condition. Higher frequencies, denominator becomes negative, larger in magnitude, tan phi equal to 0, that means phi is 180 opposite. So the mass moves in opposite force, yes, 180 out of phase. The force pushes, but mass pulls away, it's completely out of sync. So this is the summary of phase behavior. If our forcing frequency is much less than omega n, the force and motion are in sync, phi becomes 0. Omega equal to omega n, phi becomes 90 and the peak lags at resonance. And omega is much greater than omega n, then phi becomes 180, the motion opposes the force completely. This is the root cause of the most rotating machinery problems. It looks simple, radius, mass, radius, speed, but it causes millions of failures every year. Let's dissect it. What is P naught? P naught is the magnitude of periodic force produced by unbalanced rotating mass. It's also called acceleration force or forcing function amplitude. This force then acts as a system repeatedly over and over and machine spins. It shakes the system. It's not controlled. It leads to excessive vibration, fatigue, or even catastrophic failure. M is unbalanced force. This portion is the rotating system, and the rotating systems that's not perfectly centered. Even a small value like 10 grams can cause large force at higher speed, often arises due to manufacturing tolerance, wear, and dot accumulation assembly errors. So the whole rotor is not necessarily unbalanced. Correct. We shall assume a small point mass offset from the center. That's m. Radius of eccentricity. Radius of eccentricity. This is the distance from the axis of rotation where the mass is located, sometimes called eccentricity. Larger arm means more leverage, more force. Swinging a hammer from farther from the center is more impact, right? The small increase in radius can greatly increases the vibration force. Angular velocity. This is the rotation speed, radians per second. Omega equal to 5 into m is the frequency. The force increases with the square of the speed. So if you double the speed, force becomes 4 times greater. That's why vibration gets worse with high RPMs. Units of this equation. Physical interpretation. As the rotor spins, the unbalanced mass creates a centrifugal force that varies with time. The force is always direct outward from the center. As the rotor spins, its direction changes. Sinusoidal force acting on the bearings and structure. The force is what we call practical example. M equal to 0.01 radius omega. Even with just 10 grams, 5 Newton sec force is coming. At higher speeds, even it's worse. Why this matters? The unbalanced force acts on every rotation. Act at every rotation, continuously shaking the machine. Vibration, noise, fatigue cracks. Look at this equation. What force is acting on this? What force is acting on the system when it acts? How it changes with time. So it's a time varying force. It's not a constant. It oscillates like heartbeat of a machine. Why is it physically? What does it physically represent? This force comes from the rotating machine, and as the rotor spins, the unbalanced mass creates a centrifugal force. This force acts outward, but because the rotor is spinning, the direction of force changes over time. So even though it's constant, it's not. It's constant rotating frame. It's a sinusoidal stationary frame. Even though that is constant in rotating frame, but it's sinusoidal in that is stationary frame. To someone standing still, the spinning outward force looks like a sine wave, rising and falling. That's why we write. Why sinusoidal? At t equals 0, unbalanced mass is at the side. It rotates upward, force rises. At 90 degree, the force reaches maximum, then it drops, it becomes negative. The cycles, pure sinusoidal motion. The peak of oscillating force. It's fixed for the given machine, depends on how much balanced, how often, how fast. Sine of it represents the direction and magnitude of all oscillates, plus 1 to minus changes. Every moment time increases, the frequency is the sinusoid. Determines how fast system shakes. What happens if the system force goes up, then down, then up again? Each time it completes one full cycle wave, the system receives a new impulse. This repeated force causing a vibrate in response. And if this matches the system's natural frequency, that's where we hit resonance. The vibration amplitude explodes. That's why we analyze this force carefully, because it drives everything. Mathematically, yeah, smooth sine curve minus p naught to plus p naught time period is 2 pi by omega. We compress in time. It oscillates. So in this case, you see. So every moment the machine gets hit and 6 Newton force, but not constant. It oscillates 100 times every second.